Section 4.8, we're beginning cluster 2, looking at curve fitting and higher order polynomial functions. But to begin with, we're looking at power functions, the power functions. But we're looking at two things. Direct variation is going to be one of them, and then power functions. So we want to identify a direct variation and determine the constant of variation associated with it. And then properties of power functions, and power functions are defined by y equals k times x to the n, where you just have a power of x depending on what n is. N needs to be a positive integer to be a power on x. Okay, so starting off in the first example, we're in a hot air balloon and we drop our binoculars over the edge. At that moment, the balloon is maintaining a constant height of 500 feet, and the distance the binoculars are from the edge of the basket is modeled by S of t equals 16t squared. So at 0 seconds, they have fallen 0 feet, 1 second, 16 feet, and so on. All right. Now, because S equals 16t squared, we can say that the output S varies directly as the square of the input t. That's our first varies directly sentence. S varies directly as the square of the input t. So therefore, as t doubles in value from 1 to 2 or from 2 to 4, what happens to the output? So the output becomes 60, this is times 2 up here, right? Times 2 times 2. The output becomes 4 times as large. So 16 times 4 is 64. And if you check, 64 times 4 is 256. Okay, and it's becoming 4 times as large because we have the square of the input. And because 2 squared, if we're doubling something, 2 squared is 4. So it becomes 2 squared equals 4 times as large. Okay, so thinking about this, as t triples from 1 to 3, how large does the output become? How much larger does the output become? So if we compare this, 144 is 9 times larger than 16. So the output becomes 9 times as large. And again, that makes sense. So in general, if y varies directly as the square of x, when x becomes n times as large, the corresponding y value would become n squared times as large, right? Because this triple was a value of 3, and we became 3 squared equals 9 times as large when we tripled. So we're going to become, in general, if we got 4 times as big, we'd be 16 times as big for the output, and so on, n squared times as large. Okay, so that's an example of what happens in a direct variation setting, and this one was specifically varying directly with the square of our input. Now, it's not always with the square of the input. Sometimes we vary directly with something else. So in the next example, the volume V of a sphere is given by V equals 4/3 pi r cubed. In this situation, we can say the output V varies directly as the cube of the radius, right? So complete the following table. Leave your answers for V in terms of pi. So I'm not going to type in the pi part of it. We're going to leave pi in our answer. So when I write my function over here, I'm not going to put pi in it because I want my answer in terms of pi. So 4/3 pi, don't type the pi, times r cubed. Now you know that when you make your table, you're going to have pi written next to all of the outputs. So 1, 2, 3, 4, and 8, and then v of x1. Okay, now I don't like this because I want those not in decimal form, so I'm actually going to go back and do them the old way. I'm going to do v of 1 so I can get the fraction form for it. I don't have the fraction button in the table. So this one, I'm going to say 4/3 pi. Now, I could have done that one by hand. Stick a 1 in for r. 1 to the third power is 1. 1 times 4/3 pi is 4/3 pi. So I should have gotten 4/3 pi, and I'm glad that I did. Okay, so instead of 1, we'll plug in 2, and I'm going to get 32/3 pi. If I plug in 3, I get 36 pi. If I plug in 4, I get 256/3 pi. And if I plug in 8, I get 2048 thirds pi. Okay, now notice that as the R value doubles from 2 to 4, what happens to the outputs? So the easiest way to check that is just to type V of 4 divided by V of 2, and the output got 8 times as large. So as R doubles from 2 to 4, or from 4 to 8, let's check 4 to 8. If I compare V of 8 to V of 4, it's also 8 times as large. So the values become 8 times as large. Not surprising, because this has an R cubed inside of it, and 2 cubed is equal to 8. So we're not surprised the output gets 8 times as large when the input gets 2 times as large when it doubles, right? When it doubles, we're getting 2 times as large. So our output gets 2 cubed, or 8 times as large. Okay, so we can generalize this as, again. In general, if y varies directly as the cube of x, when x becomes n times as large, the output is going to become n cubed times as large. Sketch a graph of the volume function. What's the practical domain of this function? Okay, so to graph the volume function, I am going to stick the pi in here because it is part of the function. I just didn't want to have it earlier. So that's the picture of the full volume function. Although the practical, mine was a little more expanded. I just have a different zoom window, a little wider curvature on it, no big deal. And the practical domain of this function, since it's volume, is going to be that the input value r is from 0 and up. I don't know if infinity makes sense, because I guess you couldn't have an infinitely large sphere, but you can certainly have some very large spheres. So anything in this quadrant, I mean, we had a sphere that was Jupiter, and its radius was in the hundreds of millions of feet of meters, feet, whatever the units were on that sphere. So we can be quite large, and I don't know the limit to, maybe I'm going to do the volume of the universe instead, and it's going to be even more large. So we'll just let infinity be the upper boundary on that. Sound good? Okay, so let's move down to the definition here. Y equals k times x to the n defines a direct variation in which y varies directly as x to the n, and the constant k is called the constant of variation. All right, so in example, if you're looking at the s equals 16t squared, then 16 is the k value, the constant of variation. So if you're looking at the volume function, what is the constant of variation? So the k value in the volume equation is, this is 4/3 pi r cubed, it's going to be 4/3 pi. And because 4/3 pi is the numeric coefficient of the r, so this is 4/3 pi times r cubed, 4/3 pi together is the constant of variation. All right. So moving to our next page, there's an example you can read through on the bottom, and we go on to number 4 here. For each table, determine the pattern and complete the table. Okay, so first of all, it says that y varies directly as x, not as x squared, just as x. So that means that y equals k times x. I don't know k yet, though, but because I have this ordered pair here of x and y values, I can plug those in for x and y and solve for k. So I know that 12 is equal to k times 2. And so if I divide both sides by 2, I can identify that k is equal to 6. So now I can make my equation even better. This equation is y equals 6 times x. 2 times 6 is 12, and then I can fill in the rest of them. 1 times 6 is 6, 4 times 6 is 24, 8 times 6 is 48, and 12 times 6 is 72. So I can fill in the rest of the values once I identify what the equation is and the constant of variation for this specific case. So we try again. Okay, so this one says y varies directly as x cubed. So I know my function is y equals kx cubed. And then again, I have another ordered pair here of x and y values. So I can plug in the 32 for the y value equals k times 2 to the third power. 2 to the third power is 8, so 32 equals k times 8, and I can divide both sides by 8 to figure out that the k value is 4. And so this means that this equation is y equals 4x cubed. So if I plug 1 into the equation, 4 times 1 cubed is 4. And if I plug 3 into the equation, I'll need to take 4 times 3 cubed. 3 cubed is 27. 4 times 27 gives me 108. And that is my equation. The constant of variation is 4 for that situation. Okay. And the last one here, we have y varies directly as x. So this means y equals k times x. And the pair that we have is 3, 3. So 3 equals k times 3. If I divide both sides by 3, 1 is k. So this equation is y equals 1x, or y equals x. So if I plug in 1, I get 1. Plug in 2, I get 2. Plug in 4, I get 4. Plug in 5, I get 5. All right. Number 5. It says that the length in feet of a skid distance left by a car varies directly as the square of the initial velocity v. So the length L of the skid distance left by a car varies directly as the square of the initial velocity v. So write the general equation. L equals k times v squared. It's a direct variation, so it's a constant multiple of the square of v, so v squared. Now I need to figure out what the constant of variation is. I don't know yet, but I do know in the next sentence it says that if a car is traveling at 40 miles per hour, it leaves a skid distance of 60 feet. Use this information to determine k. So L is the distance, that's 60, equals k times 40 squared. So I can figure out what 40 squared is. This is, again, 60 equals k times 1,600, and I can divide both sides by 1,600. If I take 60 divided by 1,600, I get a k value of 0.0375. So I need to put this together in my equation. They didn't give me any room to do this. So we're just going to go up here. And we're going to say, now I know that the equation is L equals 0.0375 v squared. So that's the equation with the correct value in place of k for the constant of variation. Now they want me to use this function that we had no room to write to predict the skid distance for a car traveling at 60 miles per hour. So we have L equals 0.0375 times v, the 60 is our velocity or our speed, 60 squared. And so if I type that in, I will have 0.0375 times 60 squared gives me 135. And then I believe that was in feet of skid distance. Okay. Okay, so that ends our direct variation conversation for this section. Keep in mind that there are two kinds of variation, well, that we're going to study. There are maybe a few more. But we're going to look at direct variation. We're going to look at inverse variation. But inverse variation comes up in chapter 5. So we're going to want to hold on to this idea as we get towards that chapter and look at the next type. Okay, power functions. All right, so power function is any function of the form y equals k times x to the n. These are also direct variations because you can see that they're proportional. K is the constant of variation to x to whatever the n power is. So power functions would be the graphs of things that come out of variation. So we're going to look at power functions and what the graphs look like for y equals x squared, y equals x cubed, y equals x to the fourth and fifth and sixth. So I will start graphing these over here. Oops. I wanted to zoom home. You know what y equals x looks like. Y equals x. Line. Okay. Y equals x squared. I know what that looks like. Parabola. All right. Now, some of the other shapes we might not be familiar with yet, so we'll take a look at those. Y equals x to the third. Okay. Maybe I'll move this decimal thing down a little bit. Okay, so swoosh going up there. Y equals x to the fourth. Kind of like a parabola again, right? Y equals x to the fifth. Got that same sort of swooshy bit. And y equals x to the sixth. Kind of like a parabola again. So pretty big pattern here between what we're seeing with the odd and the even power functions. So we're going to summarize that down here. Okay, what is the basic shape of the graph if n is even? Parabola. What is the basic shape of the graph if n is odd? Swoosh. Okay, if n is even, what happens to the graph as the value of n gets larger? All right, so now I got to actually compare. So we're going to look at x squared. We're going to look at x to the fourth. And we're going to look at x to the sixth on the same axes here. So what's happening is that the bottom is flattening out there, and also the graph is getting narrower, so it's getting taller. So the widest one is the outermost one, is the first one, right? This one is the outermost one. Then it gets a little narrower and then even narrower, and also even flatter. So the bottom gets, big values get bigger, small values get smaller. There, okay? So as the n gets larger, the graph gets steeper and flatter around the origin. Okay, large values get larger, small values get smaller. Write that in. Okay. If n is odd, is the function increasing or decreasing? Okay, so this function, this shape, is always increasing. The entire life of this function is increasing. It's going up rapidly, then it slows down, but it's still going up, then it goes up rapidly again. Okay. Use the patterns from problem 7 in combination with graphing techniques we learned previously to sketch each of these graphs without using a calculator. Okay. I better draw in some axes so that I can do that. Y equals x squared plus 1. This plus 1 is an upshift. It's going to shift my vertex, my y-intercept up 1, but I'm still going to have that parabolic shape. But I'm not going to touch the axis right here. Okay, do it again. Better put in some axes. This negative coefficient, that negative coefficient is going to flip it downward. It's power 4, so I'm going to make it pretty steep with a flattish middle. Okay, but it's going to flip downward because of that negative 2. Okay, let's get some axes going in here. This 3 is going to make it narrower than usual. This 1 is going to push it up. It's going to be facing upward. It's going to be pretty narrow. And it's going to have a really flat bottom because of the 8 for the power. Again, rough graph. Graph it on decimals if you want to check it. Okay, this negative is going to flip this over. So instead of an increasing swish, it's going to be a decreasing swish, and it's going to flatten out there. Really tight to the x-axis here because I got a 5, which is a power bigger than 3. Okay. Power 10. Oh, okay. So I know power 10, my parabolic shape is going to be very steep and very, very flat. All right. And then 5 means steeper than usual. 2 means up higher than usual. So I'm going to have my swish shape, but the swish part's bumped up too. Ta-da!